So let's start the DCMotor2 then. Yeah. So the DCMotor2 mainly looking into the control method. How we're going to control the DC motor? Probably in the past you may have done some DC motor control. In here we're going to look into about the DC motor, mainly about the modeling, and also various type of the control method. So firstly, let's see how we're going to drive a DC motor. The method to drive a DC motor, and I think for last lecture we mentioned about we only use a DC voltage to do that, but of course it won't be that case. In the lab, we usually use a DC motor like a DC power source, adjust the DC voltage, but that is only for experiment. But in fact, we should use a power E driver to control voltage. And then to break a motor, we also need to go through how we're going to control to break the DC machine, DC motor. So to join and break a DC motor, in here we try to show the concept, how we're going to do that, what kind of concept behind we're able to join the motor and break the motor using a power driver. You see a power driver, you only provide them with a DC voltage. And then can you tell me about if you want to power up a motor and to break a motor, what's the difference in the power source? How are we going to do that? How are we able to what kind of signal we're able to provide from the DC source to the motor in order to motor and break? What do you think? Do you understand my question? Sito, could you answer that?
Yeah, I think the source will be the same, just for
the driver is the same, yeah.
With example, we have the DC motor and we have the voltage source. And when we want to drive it, it's the one direction, and we have a signal. And if we want to break it, we just need to change the signal and make it.
How do? That's what the question is. The motor is the same, the DC source is the same, but how we control from the DC source the motor to make the difference between motoring and braking. What are the difference?
The current flow.
How do we change the current flow? You see, the DC source is a voltage source.
Yeah.
The motor is some winding.
Yeah.
And then how do we change the current? Motoring, the current will come out from the DC source to the motor.
Inverter.
Braking, of course, will be reverse, right?
Yeah.
Or would that be reverse? Yeah, yes, I think so, right? So how do we control them?
Just like to switch on and switch off the.
No. We always switch on and off. The concept will be how we're going to control the DC source to make it become breaking the motor, right? That's the question. Yeah, I think you all has been studying DC motor for quite some time. You understand them, but now then you come to a stage, what's the physical phenomenon? We're going to control the motor to become motor and brake. What's the difference? So you need to ask yourself, how are we going to do that? Unless you answer this question, then you really understand what's the real operation for this motor. Okay? Since you're still not quite sure that, how about Sheldon? Can you answer that?
About the difference
between motoring and braking when you connect DC source to a motor?
I just think if we turn off the power on, then the motor will be generation.
You don't think about, are we going to turn it off completely? No. So there's a way to manipulate with the DC source, right?
Maybe use the inverter to make the opposed direction current going with the
inverter is AC.
Yeah.
We're still using a converter, right? I mean, inverter is term, but that's what he's trying to say will be how to change the current. That's the thing you need to do. I think physically you like to reverse the current so that you're able to break the current, break the motor. But how are we going to do that? What kind of mechanism? So now the question number 3 in here. And how a motor will become a generator? What's the difference? Do we do something to the motor in terms of the electronic?
Giving some bolts to the motor, so this dictate the motor.
Mm.
However, if we spin it to some kind of, what you call it, to some shaft or some other way, if we start moving the motor, then definitely interact with magnetic field, and then it works.
Not go to that point. I mean, well, we all know a motor, we have magnetic field, we also armature current, we have DC source, right? We need to manipulate with these three items in order to control the motor become motoring or reverse, that means reverse motoring, or could be regenerative. So there's quite a few operations. So of course, in the next few slides, we're going to show you a few basic operations. So now then, these three questions will therefore examine you how good you understand the operation of a DC motor. Although you always say, oh, DC motor is so simple, we learned in the past for many, many years, in undergraduate, postgraduate, but now you come to a stage, you need to answer them. Maybe in the future, when you become a professor, your student will ask you, look, how we make the DC driver or DC voltage source to do that job. And next thing to tell you, we do have an inductive component, right? For last few lectures, since we don't consider the inductive component, why is that? Why we don't need to consider? Do we need to consider? And when do we consider inductive component? Sheldon, you have been doing some motor or inductor, so tell me.
Okay, the mighty is an inductive component. Sorry, I don't understand actually when we.
So for last few lecture, we've been working on the DC motor equation, right? Input voltage equal to the voltage drop on the RA plus the back EMF. We haven't quite manipulate or operate on the inductive component, the inductor LA, right? But so how is that inductive component being used? Why we don't consider last week, but now I'm asking you how the inductor affecting the performance of the motor. When do we need to consider inductor, or when do we not to consider inductor? I think when you go through many textbook or literature, sometimes they use LA, sometimes they don't use LA, right? When do we do that? Which analysis we use, which analysis we don't have to use?
When we consider some losses or consumption of some magnetic, we use LA.
Inductive have low loss. Inductant have low loss. The inductor, that LA inductor, supposedly will be appear in the DC motor. But last week we did not mention it. We just mentioned we did not put them into the motor equation. But today we're going to do that. So this question asking you will be, when we need to use the inductor? How? So you don't need to answer me. I posed a question to you to ask you how much you understand the DC motor. Yeah, after this lecture, you will understand. So that's why my target question here is to see how good you understand about DC motor. Maybe you've done it in undergraduate, but now then when you come back after a few years, I will ask you again, your concept for DC motor may not be so good. Sorry to say that. That's the thing I try to look into that. Yeah. And the next thing will be how we're going to control motor torque. Of course, we've done that. Now we examine about control torque. And then what's the basic principle? How we control the motor. So that's a few items we're going to study in this lecture. Anyway, so today we're going to a few topics. Operation, what different kind of operation we may have, and the basic method we control motor, control the voltage, and then that's the thing we try to look into, and dynamic operation for the DC motor. So first of all, for DC motor, then what we're trying to do will be for DC motor, definite DC motor control, we'll be trying to operate the motor in order to control its more precise mechanical output. We can control the motor for rotational, but nowadays we try to be more advanced control, like even though the angle, position. For rotation motor, we tend to control the rotation angle, but for linear motor, we try to control the linear position. For 3D motor, we control the solid angle, right? So that's another thing we need to control, rather than just control the speed, right? If you see if an electric vehicle, we only control the speed, we may not able to break the vehicle in the exact position. If we use motor for a robot, we need to do the exact positioning for the arm movement. So that's why motor control is more than that. And because of this one, we try to develop some electronic, high power, low power electronic, like the microcontroller system, try to bridge them to control with the mechanical system. And then for motor, then it's from electrical to mechanical. But all the motor can also behave as the generator if we reverse that. So 99.9% of the motor in the world can do both jobs. So that is to say, you can see that fundamentally, we not just control the motor on or off. I think in many years ago, probably 50 years ago, when we had motor, we want to control speed, we just turn on and turn off using this zigzag control. We try to stabilize the motor at a certain speed, but that's a really old method. But nowadays, we're more talking about intelligent control, precision control. That's something we need to look into. And more also a motor drive system, mainly talking about protection, how to ensure the motor and the electronic are under good protection, including we don't have any overcurrent, over voltage, over temperature or under temperature, or maybe the excessive current, especially during the start of the motor or braking the motor or motor stall. We all need to under protection, not only just operate that. So that's the thing we need the performance from the motor drive system. So the key thing we try to operate for the motor should cover the basic four, five items will be speed control. That's basically all the motor rotating at a certain speed, and then we look into that. And then we should use some modulation waveform, modulation power to do the job. And then directional control. So motor, we got different kind of direction, forward, backward. Even though for linear motor, we also forward and backward, we need sometimes we need to reverse the current direction to assist the motion. Braking, so we rather than brake the vehicle, brake the motor completely, we usually talk about slow down the speed and also control the stopping distance and time. And operational, we need to sometimes combine with the motoring and regenerative together. Like if you have been driving an electric vehicle, you know that when you press the gas pedal, then now should be accelerator, then the vehicle will go forward. And then when you release the pedal, then the vehicle is not stopping instantly, but you go to power regeneration. The vehicle is still going forward. The motor is still rotating forward, but now the energy will be returning to the battery. So that's a kind of the operation mode. And position control is important. Nowadays, all the motor, we need to really call the precise motion control. Precise means even though the motor, for linear motor, for instance, we should able to control the motor precision down to anybody can tell me what's the common precision control resolution? 1 mm, 1 inch, 0.1 mm. What do you think? How is the popular precision control down to 1 mm? 1 mm? So you think 1 mm would be enough for robot control? That would be good, right? So what do you think? How?
Maybe 0.1 mm.
I don't need to ask you, I think you put it that, but you tell me an answer. What do you expect the precision control?
Within 1 mm. It depends on different work background.
Of course, all different different background. But now then, when you talk spectrum for precision control, then we use it down to micron, 1 micron.
1 micrometer.
1 micrometer.
How could that?
That technology has been done 30 years ago, not to today. The team in my former university and team in Shenzhen University have been doing that 20 years ago. It's an old technology, really old technology now. Precision control 1 micron. You can see that that is for fabrication, PCB fabrication or semiconductor fabrication. We are talking about the nanotechnology down to a few nano. So that is to say the semiconductor is now so high resolution. So our precision, how to place the component, soldering, and then etching, we need to down to micron, maybe less than 1 micron, in order to have so high precision to place the component to do the etching in the PCB fabrication. That's the basic requirement. So that's why precision control is so straightforward nowadays. Not to 20 years ago, I think if you see my research paper, we published hundreds of precision control paper. We are able to control a motor in high precision. Linear motor, 2D motor, right? That's the thing we have to do. So precision control is so important nowadays. Of course, a robot, we don't need high precision, but if a robot going to work as a fabrication to place whatever dedicated component we need that. So how to do that? That is some technology, not in this lecture, but probably next few more years, when you have a more deeper understanding for motion control, you may know how to do that. So that requires how to design a motor, how to design the control, right? Anyway, so for really basic operation for motor will be like that. The first one will be motoring. So that means we provide DC voltage, the motor move forward. That's it, very straightforward. So the motor current IA will be positive. So fair enough, that's the most common way to do that. For instance, electric vehicle, you catch the accelerator, the motor go forward, the vehicle go forward. That's a so-called motoring. And then we generate braking. That means now you remove the pedal from the vehicle, and the vehicle will return its dynamic energy, rotation energy back into the battery. So that's also called the regenerative braking, or when you try to reduce the speed for a motor, then the energy from high speed to low speed, there will extra energy. The energy will not disappear, will return to the battery through the motor control system, or so-called motor driver. So that's called regenerative braking. Dynamic braking, we do more than that. We use some more additional item to stop or to brake or slow down the vehicle, including maybe some kind of way to dump the energy of the motor in another means. The second one, regeneration, that means the energy will not be lost. We return to the power source, maybe the battery, maybe AC source, maybe DC, so wherever the source is, we able to do that. And then the third one, dynamic, will be we try to disconnect it from the source, and then its energy will no longer return to source, but instead we connect something to dump the energy, like resistor, like other thing. So called dynamic braking. The last one, plugging, means we'll try to stop the vehicle, but using another more aggressive method. Reverse the polarity for the motor, and then we drive the motor reversely, force the motor to go reverse. So that would be more aggressive. The motor can quickly reverse or brake or stop quite instantly. So that's a 4 basic method. So these 4 are all the basic motor operation. All right. So let's look into one by one to see which one is which. So first one, motoring is quite common. You can see the diagram here. Then we have a motor, we have back EMF, the battery here. I use a battery because the DC source can be anything, right? So, and then the voltage across here will be all flowing in here. The current IA is positive. So motor, we prefer separate sided. So in this case, we have another field winding to provide the magnetic flux to the motor. We can also have a DC source or to provide the field current. So that basically will be the operation for the so-called motoring mode. And the current IA will be as such. You can see that the equation for armature current obviously will be input voltage from DC source minus the back EMF divided by the RA. So that is how we look into the motoring, the equation, right? It's very simple, straightforward. That's all the basic operation. In here, you can see that because the power source, it provides the motoring, so the V in is greater than EA. So that's one of the features we can see from the motoring. So now then, you set up the power source in such a way, you drive the motor forward, and the motor current is positive, IA is positive. So next, we just imagine if now I want to go to regenerative braking, slow down the vehicle. If I'm driving an EV, I remove my foot from the pedal. What happens next will be this one. Then you can see that if you do that, then the phenomenon for regenerative braking will be the back EMF EA voltage is higher than the input source voltage. Because of this one, then the current will reverse. So if you look into the power management, obviously, this looks like a voltage source from the motor. And the current coming out from here. So that means this motor or the back EMF unit will become a generator because the current comes out. So that's so-called the regeneration. That's how the regeneration come out. And then you can see that the current IA is going into the DC source. Yeah. Go into V in. That means we are now charging the battery. You get that?
Yeah.
So then you can also see that the current is now reversed. So the feature between the motoring and regeneration will be the current reverse. Ali?
Can you explain a little bit more, like when we like this regenerative braking happen, once we take off our foot from the pedal, so okay, now we are not applying any source. So that's why source voltage is lower
No.
than the back,
Yeah.
right?
Exactly. That is the way to control the motor. You mentioned a really good point, how we control motor. Before you talk about that in the introduction part of the question, you can answer that. Now you can answer one. So that's the way we control the DC motor driver. In order to make the system become power regeneration or regenerative braking, what we need to do to control the DC source to drive the motor to lower the voltage than the EA. That's the control system like. So that's how we manipulate the motor driver to deliver lower voltage. Then you go to regen braking. If you want to have further braking, further lower. So how much you trying to regenerate depends how much you lower the incoming voltage to force more current to go back to the DC source. So that's another way we can brake or slow down the vehicle. So obviously you can see that the armature current, IA, will now become EA subtract V in divided by RA. Yeah, obviously, because EA is high voltage, the input voltage, we control it. And the current becomes reversed. So now that this becomes generator, this will become being charged. So that's how the operation looks like. You get that? So now after this lecture, you now fully understand how we control the motor from motoring and regeneration. So that's the two really important and basic always happen for all the motor drive. Not only the EV, industrial drive, everything must have these two operations. Otherwise, it's not a motor. For all the motor drive, it must have these two operations. And how to make your motor driver to decide like this? Mainly about the driving voltage. Control driving voltage higher and lower in order to control motor forward and regeneration and braking. Okay? Now you fully understand. So after these two major operations, next operation is dynamic braking. So there's many different ways to brake the motor, including in here. Instead connect a DC source to the motor. Now we remove the DC source, but instead we putting a braking resistor like this. So that means the energy must be coming out from the motor and dump it to the RB, the braking resistor. We don't return energy to DC source, so that's not regenerative braking. It's only called dynamic braking because we dynamically to brake the vehicle and dump the energy into the resistor. And then we can also adjust the RB. We adjust this RB in order to control the amount of the braking. Obviously, if you consume more energy into the RB, you have braking it further. For instance, you can increase the braking current RA, then you can dump more energy, take more energy out from the EA. So
with our normal cars, which is not hybrid, this happens.
yes, normal car we do have this one. That is the design. And I did not cover that in the electric vehicle lecture last time, but it's more detailed design. But in the future, when you work with me in PhD in electric vehicle, I'll show you how to do that. Most of vehicles should have this one. I'm going to talk about why we have that one. One question will be, if I want to brake the vehicle seriously, do I increase the RB resistance or decrease the RB resistance? What do you think? Increase the resistance? Okay.
If you increase them more,
I square R, right? More loss go there, right?
Yeah.
Okay. So, Sitao, what do you think?
So you wanted to break the
More seriously,
more
break the vehicle. So RB resistance should be higher or lower?
maybe from the we need more time, that's mean more energy go back to the battery, that's mean more mechanical energy become the that we break. So
We have no battery here. We just dumping the energy into the resistor, right? In this diagram, we have no battery anymore. We just, you see, starting braking, we remove the battery, putting a resistor there.
the break. Yeah.
You haven't quite answered my question yet. I asked Xiaodong, what do you think? If you want to brake the vehicle seriously, aggressively, do I increase the RB resistance or decrease the RB resistance?
Decrease the RB.
And I feel like
Decrease.
Yeah, okay.
Yeah.
Think about it. If you decrease the RB, you draw more current IA from the motor. Does that mean you're taking more energy? Yeah, you want to eliminate all the energy from the motor, right? The motor is a EA, right? That's the better way to brake the motor seriously. And then when current becomes so large, the I square R be still large anyway. So now come to another issue will be, why we need that? Why don't we use the battery? Regenerative braking. What scenario we need to do that? Would that be so stupid? We just raising the energy into RB? Why don't we just using 2.2 regenerative braking for the vehicle design? Under what situation we do that? Do we do?
Don't need when battery is already full.
That's a good point. All the vehicle, they need to make some reservation, some kind of insurance. In case the battery full, what can they do? They cannot say, I put more battery. Because battery is so expensive, with a limitation of the battery. But the resistor, only a small, tiny resistor, you can you put it there, but you have additional insurance. In case you fully charge the battery, and then you live in top of the hills, and then you need to go out, and then the vehicle automatically go to regeneration. Then the current still continue to charge your battery. That will be a disaster. The battery will full. Your BMS stop you to do that. Then you cannot brake your vehicle. So of course you can use your big pack mechanical brake to do that. And another way will be you can use the RB to brake it. So all the vehicles, they do have RB installation, just in case if the SOC is too high, then you tend to use RB to brake it. And of course, RB, you need to have a really good cooling in order to make sure RB will not too hot. So that's another way to brake it. So that means a vehicle, they got different way to brake it. Regenerative braking and also dynamic braking, of course, the mechanical, the big pack, the normal thing to brake the vehicle. The next one will be the plugging. The plugging is obviously something here. We reverse the polarity for the input source. So that's to say we tend to reverse the motor rotation to reverse direction. So that is to say you're able to brake the vehicle rapidly. Of course, in here, we not tend to reverse the rotational, we just reverse it so that motor will quickly reduce to zero speed. Just when we reach the zero speed, we need to stop to avoid the motor go to reverse direction. So that's a much quicker way to brake the vehicle. But the disadvantage is
It will affect the performance of motor.
what performance?
The life cycle of motor will be because you are stressing, putting too much force on the motor by
From the equation, why we have more force and more stress to the motor? Why? That's from that equation. Now the back EMF like that. You reverse the input voltage. And then you can see that this and that are in this loop will be the same addition of polarity. So we're now doubling the source DC voltage. All this summation voltage will go to the resistor, RA resistor. What's RA resistor? Is the armature resistor, the internal winding resistor. So that means we are doubling the current to the motor winding. The motor winding will get really hot. We're not transferring energy to a DC source, back to the battery. We're not doing that. We're just forcing the motor current to double the current. So the motor will get really hot. Although we are able to break the motor quite instantly, rapidly, but the disadvantage will be we are damaging the motor. Not really damaging, but it's just not good. If it's too hot, the motor will need really good cooling, or may need to be careful about the overheating of motor. You need additional cooling. So that this kind of plugging mode, we don't use them often. We only for some highly emergency, we need to do it. The motor drive we have that capability. In case anything sudden braking. So when we press the right-hand side pedal, that's normal motoring and regeneration. And the middle one, or the left-hand side one, which is the braking. The braking will have three kinds of the capability. One will be mechanical brake, dynamic braking, and also plugging, depending on the vehicle design, how you design it. Okay, so that means normally the right-hand side pedal is the normal good operation. You won't have any damage to the system. You won't have any aging. It's good for the vehicle because you're using normal motoring and regeneration. But the left one will be something not really good. We tend not to use it. So when you drive an EV, many people only using one foot because that will be good enough. Of course, in some more emergency, more instant braking, they use the left pedal. So that's the operations. 4 major operations will be all the motor will happen here. So you can see that for all the case, we mainly how to control the motor voltage. Of course, dynamic one, we tend not to do that. The dynamic one, so this will become resistant. We can still do that using spun power electronic to do that. We use the dynamic with additional switch here, connect with a resistor. In case we need to use resistor braking, we disconnect the source and then connect a switch here to do that. So here dynamic braking. So this one will create different voltage to drive them. And then for dynamic braking, so we can therefore do that. We don't usually use that. In case anything happen, we can turn on the RB to brake the vehicle quite rapidly. And then in here, we need to adjust all this waveform so that we have this kind of duty ratio will be moving. Then we're able to control the output voltage. So that's how basically we are trying to now discussing the motor driver, the so-called power driver, how to drive the DC motor. So the usual waveform will be switching waveform, so-called the Peter waveform, this kind of switching waveform, so-called the power electronic switching waveform. And then we don't use linear voltage. I think you all know that all the power electronic driver are switching waveform. We don't adjust the DC voltage totally because no way we can adjust DC voltage unless we use a resistor as a potential divider to adjust the voltage. But that won't happen anyway. We cannot use transformer to adjust the voltage because we cannot adjust the tapping. It's not auto transformer. So the only way we do will be using power electronic to control the output voltage. So here we're going to study a little bit more about the power driver, how we're going to adjust the DC voltage to the DC motor. So I think that's quite straightforward. And so this is those waveforms we're going to apply in press to the DC motor. So you can see that if we have this kind of switching waveform, the amplitude is V on, and then we have the duty ratio, this way duty ratio, T on divided by TS will be our duty ratio. So this duty ratio, in theory, you can control it between 0, 1, yeah, that's it, all the range. So that means the average voltage, so V average will be equal to duty ratio multiplied by V on. So that is to say we're able to adjust this average voltage from 0 volt to V on voltage. So that's quite a wide range of voltage control to the motor. Then you may ask me why we use square wave. We're not using a DC to do that. If you use a DC to drive motor, of course we have a DC voltage to drive a motor, right? How are we going to make the DC variable voltage? You can't make it variable. You cannot use a transformer, right? You don't have variable voltage transformer. You need to use your hand to move the coil. I mean, we are not doing hand control. We're doing electronic control. Impossible. And we are not going to use resistor. Of course, you can do using resistor. But how are you going to change the resistance? Use hand control? Impossible. And then you are wasting the energy. So that's a huge loss in here. We don't like that. So that means that is so we need to think about, so this will therefore become power electronic to control voltage. So that's the method we do. So the method is called pulse width modulation to control the pulse width in order to control the voltage. And the motor itself, many students may ask why we can apply a square wave to the motor, not DC. Would that be a problem if the motor we are using a PWM square wave instead of DC? Do you think a motor will be good when we're using a square wave? Which way is better, square wave or DC to a motor? Xiaodong, what do you think? Why?
Why it also has some inductance.
Mm.
We using square wave to drive more.
Yeah, that's a good point. You see a motor usually is considered as an inductive component. Internally, you got to be inductor. So this kind of the square wave, you can filter out by the inductor, smoothing out. So that means the motor itself will not see this kind of the switching waveform. It does see the switching waveform, but the motor itself only needs the excitation voltage, the total excitation of the voltage. So that means they only need to look into the so-called volt second for the voltage. So and then you can see that. So the inductor itself, they only looking into the volt second, voltage times the duration. This will generate to us about the flux linkage to the motor. The motor itself doesn't really understand voltage. They only understand the magnetic flux, total flux linkage to the motor. So as long as you vary the voltage, and the time, the motor will experience different kind of the flux linkage. And then that will give the motor operation. So that is to say, even though the switching waveform doesn't matter, the motor doesn't understand it. They only understand the flux linkage. So that's why we can do that. So for this kind of PWM, can be any PWM, can be as narrow as this one. So although you know that, we quickly to remind you what it is. For instance, we have some switching waveform as such, T1, T2, T1 0.2 ms, T2 0.8 ms. We are asking the duty ratio, the period, frequency, and the average voltage. That's straightforward. The duty ratio is T1 divided by total time equal to 0.2 divided by 0.2 plus 0.8 equal to 0.2, 20% duty ratio. So motor drive can be 20%, can be any percentage. And the period, the switching period here is T1 plus T2, equal to 1 millisecond. The switching frequency here will be 1 over the TS equal to 1 kilohertz. Average voltage, now then we become peak voltage multiplied by 0.2, become the actual average voltage applied to the motor or this kind of the waveform. So 1 kilohertz is one of the typical frequency we drive a motor. But next question asks you, do you know what's the typical frequency range we drive a DC motor? What frequency we usually drive a DC motor? Do you think 1 kilohertz is a good frequency? Do you think 500 hertz? 5 kilohertz? 10 kilohertz? 1 megahertz? 100 kilohertz? What frequency? Sorry, 1 kilohertz is enough?
It's
Enough?
not good.
It's good enough.
No good. Not good.
Not good. What frequency do you think?
Or maybe it's just a very little point because we can hear to 20 to 20K. So maybe need to greater than 20K.
Okay, that's a good point, but not always like that. Many people say human is 20 kilohertz is the upper limit. So any frequency more than 20K is good. But 20 kilohertz is sometimes will be slightly higher for many high power motor drive and also motor. For low power motor or some kind of actuator or servo motor, of course we can go for more than 20K. But you can see that in many commercial inverter to drive industrial drive, like 100 kilowatt of motor or 50 kilowatt motor, then you may not able to see too many of them are higher than 20 kilohertz or much higher than 20K hertz. So that means you can see that also for instance, for train, because such a high power, we may have difficulty to drive at more than 20K because the train although we can use IGBT, but still many trains are using GTO, MCT, so they're not good at such a high frequency. So that means this kind of the motor drive is quite a wide range. For really high power, we can only use 10 kilohertz, although we can hear, but not that serious. Although we can hear 10 kilohertz, but for all the adult probably will not hear it properly, and the noise level usually will be quite small anyway. And then for robotic control, really high frequency, then we can use more than 20K, 50K, 100K, that also be okay. So that is to say, 1 kilohertz is really, really high power. Probably megahertz will be megawatt power, we use 1K, but usually can be from 1 kilohertz up to 100 kilohertz will be also commonly being used. So don't think about we always need to more than 20 kilohertz. We like to, but probably we cannot always do that. So here we'll show you a typical motor drive system. So let's see how that motor drive system working. So as you mentioned before, we want to apply to the motor voltage to be a square wave. So instead using a DC source directly the motor, we're using that switching waveform. So obviously you can see that when this turn on, then the DC voltage applied directly across the motor connected. and then the dial will be reversely biased. So that means when this is turned on, motor voltage equal to DC source voltage. This case. So next, when we turn off. So when I turn off, of course, we don't have any VDC voltage applied to the motor. Instead the motor, and then I say here, Vm equal to 0. Why is that? Anybody tell me why Vm, when we turn on the switch, S will become 0 volt?
We have this open.
Yeah, when S is open, turn off. When S is open. Why I say Vm equal to 0? Why Vm, can't Vm be other voltage rather than 0? But just now we're using that is the circuitry here. That's a really typical, really highly common motor drive to all the DC motor, really common one. And then just now I say when we turn on S, when S switch is turning on, of course the motor voltage equal to VDC. We all agree with that, right? You agree. But my next question is, when I turn off the switch S equals 0, turn it off. When this off, of course, we cannot have any current in here. This current will become stopped. Then I say Vm voltage equal to 0. The motor voltage equal to 0. Why is that? Why the motor voltage equal to 0? No current in the
circuit motor. The series dial.
no current.
Yeah.
The current still. Do you think the current IA will disappear?
So
No,
the current
that is.
direction is reversed.
Do you think the current IA will reverse? No. The internally the motor have a large inductance. Usually when we have a large inductance, the current cannot stop or reverse instantly. As soon as you turn off the S switch, the IA current still need to continue to flow for a short period of time because its energy is there. You can see that the motor when it rotates rapidly. If suddenly we remove the power source, like the S being taken away, the motor will not stop instantly. Will still must be continued to rotate for a short period of time anyway, until the friction slows it down. And then if the motor continue to rotate in the forward direction, and then the back EMF is proportional to omega, right? I think you know that back EMF EA is equal to K phi omega. So omega cannot instantly change to 0. So this still have some omega there. Look, maybe high or low, maybe slightly lower, right? So the voltage will not disappear instantly. And then, what do you think the current?
Same.
Yeah, the current, because internally we got our inductor LA here. The inductor holding the current to still continue to flow forward. So our IA cannot disappear instantly. It's not resistor. Pure resistor, the current can disappear instantly when the voltage disappears, right? But not the IA. So that means in here, my comment here, Vm equals 0, because this current continue must be here. When this stop, the current cannot go away, it's just looping in here. Looping the dial, the current looping with the dial. Then when the dial conducting, the voltage will be really, really small, only 1 volt, maybe 1.7 volt, maybe 0.7, we are considered as 0. So these are dial conducting. So when the dial conduct, of course, the Vm voltage equal to 0, right? So now then we can see the public logic will be the motor voltage when we turn on the S, turn off the S will affect the motor voltage equal to input voltage VDC or 0. So that means the waveform must be more look like square wave. Then we can say that the average voltage. So that means if the voltage will be like that, huh? So that's the voltage. So that means the VM voltage we turn on, then the voltage equal to VDC. So the VM voltage, then 0, VDC 0. So that means when you average this, then we multiply by the duty ratio. So the motor voltage will equal D VDC. So that's to say I can adjust the duty ratio to control voltage impressed across the motor. As I mentioned before, the motor doesn't understand anything about the square wave or DC. It only understands FA voltage, which is the first linkage. So in this case, the motor will experience D VDC voltage instead of the VDC, sometimes this amount, sometimes 0. It doesn't matter. Motor don't care. So that's the basic principle.
What D
Duty ratio.
yeah.
Duty ratio here. D here. I just mentioned about here. Duty ratio is the pulse rate here. Okay. Duty ratio. Turn on, turn off. Okay. So that means it only be controlled by the duty ratio. So the motor voltage, now we can see that will be only controlled by the duty ratio. We can adjust the duty ratio from 0 to 1. We can therefore obtain the voltage to the motor from 0 to the peak voltage. So that's a nice thing to have. So you can see that we now just using a simple transistor with a diode, we can able to create a square wave form. So this circuitry is really the most basic DC motor control. We call it the simple chopper. It's simple. We call it chopper. Chop the waveform. So if you any power EPO mentioned to you, this is so simple chopper. Okay. Simple chopper is a typical controller name for this particular application. So let's look at this. So if you got this simple chopper, we try to apply to them. So let's see how the power look like for the system. So the current here, say coming out from the DC source, I use lowercase here because the current is not a pure constant DC, it's variable. When I say something variable, changing current, then I will use lowercase. If something fixed, like the battery voltage is fixed, I use uppercase. There's some terminology I use here. Also, many people are using this terminology. Uppercase means DC, constant, fixed, unchanged. Lowercase means AC signal or changing signal. So IAC here. So that
You are saying DC is changing?
yeah. So I use uppercase here. V is uppercase. That means it's a fixed, unchanged. And when I say unchanged, it may still change, but not an AC signal, a more DC quantity. And then if something like sine wave, square wave is changing, then we call that we using lowercase to represent the parameter. So we know that this IDC we're going to have some kind of the maybe switching waveform. So I use lowercase in here. And IA here I use lowercase. Last week I used uppercase, but now I use lowercase because we know this current may have some kind of the variable later on. So let's see the current in the DC source. The current in this DC source IDC here. Then will be integration of the IDC with the time. Yeah.
So one question, like though IDC is constant, capital one, but
Capital,
upper
like 15 volt
yes.
or 20 volt. Yeah.
But
Something
you
like
think it is changing just because of that chopper, it's keep changing. So that's why you are saying we are using small like lowercase letter.
yeah, you can see from this waveform here. IDC, when I turn on the transistor, the current, when I turn off, the diode is looping. So that's mean IDC, this current,
First half, it is uppercase letter DC, but for when it is off, then it changes to zero. So
zero,
it keep
because,
changing.
on and
That's why
off,
we
on and
use,
off, then it's square
lowercase
wave.
letter.
Yeah, I use lowercase there. That's it. Some just ensure, make sure that there will be some variable, the changing signal, not a constant fixed parameter. Yeah, that's usually is my terminology. My way to distinguish between AC signal and DC signal. So that's why now then I want to get the average current. What's the average? So now then I get in here. I integrate IDC in here. Then of course, obviously, that will equal to multiply the duty rate ratio. The amplitude here, this level, you call it this level, same as this level, and anyway. And then the power, the DC source, this power, of course, equal to DC voltage, multiplied by this one, multiplied by the average current. So that means the power from the DC source will be VDC times IA times D. Fair enough. So of course, you don't really need to integrate that much because you can see that it's a simple squaring. You can, in this integration, you can simplify by using IA D anyway. That will be good enough. Okay. But of course, if the waveform have harmonic or many other components, you may need to integrate it. So that gives you thinking about if the current in the DC source squaring, then the power level will be much lower because you have duty ratio component there. The voltage is unchanged, but the current will become much lower using the duty ratio to average it. So that's how we can see the behavior of the PWM waveform. I think you know it, but in here I'm using square wave to make sure that you understand how to calculate average current and also power. So that means in ideal condition, then the switch will perform by a transistor. So that transistor is IGBT. So DC source in here go to the motor. So the whole motor, the input voltage for the motor will have component RA, LA, and the back EMF. So when transistor turn on, the whole source voltage VDC will appear across the V-in. So V-in will therefore equal to VDC. So that is to say, you can see here. So here we got armature current. And DC source current, IDC, would therefore just mentioned to you with a square wave. And then when we turn on the transistor, then of course this voltage across the motor, the motor consists of the RA, LA, and back EMF, right? Three components together become your motor. So the motor terminal will see this V-in voltage. This V-in voltage will therefore equal to the VDC in here. So the amplitude equal VDC. And then next, so the transistor voltage, VQ is the transistor voltage. When we turn on the transistor, the voltage across the transistor supposedly will be really, really small because turn on a switch, then it will be 0 volt. So voltage will be more like 0 volt here.
Turn on or
turn on the transistor Q. Turn on this transistor, like the switch. We turn on the. You remember that we turn on the switch here, but now we replace the switch by a transistor. It's the same. We play by a transistor. When we turn on, of course, 0 resistance. Then of course across here will be 0 volt. So the voltage across here will equal 0. You get that? So now then, that's how when we turn on. So next, if you want to turn off, right? Turn off the transistor. So when this being turned off, so now then when this being turned off, what happened here will be IDC will have no more current equal to 0. So now equal to 0 here. Yeah, equal to 0. And then because 0, and I say this current are looping in here, so this voltage equal to 0. So now this equal to 0 in here. And then when this is 0 volt, equal to 0, this equal VDC here. So it looks across here. You turn off the transistor need to stand for all the voltage. So what the voltage across the transistor equal to VDC anyway. Yeah. Yeah. You get that? VDC, this voltage, VDC voltage equal voltage VQ plus V in, right? Yeah. Kirchhoff's law, right? So now then, this equal to 0. So that VQ voltage, therefore equal to VDC. So now then VQ voltage equal to VDC. The transistor voltage equal to VDC. That's all. So just show you here about all the waveform, no matter voltage current in all the other transistor or current, they all look like square wave. Okay. But having said that, but the current, armature current here, still a DC current. Because internally is inductive, we need to have the current so that the motor can continue to rotate forward. Yeah. Because we know that the motor is doing a certain operation, maybe providing a torque, providing a frictional torque to make the motor rotate forward. So because the torque equation equal to K phi IA. Yeah? So that means when the motors continue working, there must be torque in the motor. The torque cannot disappear, so the current must be still there. So the current will be nice and linear, constant.
But current value will not change when we turn it off.
Of course, gradually current will change, but when we're talking about here, this time domain, how much time we're talking about? We're not talking about a few minutes. We are talking about, say, 100 kilohertz. That will be 5 microseconds here. So instant, the current cannot change. That's what the domain we're talking into, the switching waveform. We're not talking about you drive the vehicle for a few seconds, a few minutes. Then, of course, the current will change. But when we look into the micro switching, that's how the operation. The IA will not change within that time domain. Okay? IA, do you get that? So what we're talking about here will be the switching operation of the transistor to the motor, how they look like. Okay? The current, of course, always change. When you move the vehicle after 10 seconds, you're going to overtake another vehicle, then the current will change. But within 5 milliseconds, 10 milliseconds, it's not yet changed. Okay, still quite a constant. Anyway, any question up to this point? So this gives you a really basic operation for this motor, how we interact a motor to get a basic motor driver. Here I use a really simple chopper to show you how the transistor on and off to provide variable voltage and how the basic operation for DC motor look like. Okay. So in here, I still assume that IA is fixed constant, but later on I may not be doing that because I know that we have an inductor here. The inductor could vary the current to become have some ripple. Later on, we'll look into that if there's a ripple, what will happen. But anyway, so that means the average voltage of V in, average voltage V in, average voltage to the armature voltage. So the motor voltage is square wave, right? So this motor voltage will therefore equal to VDC from the source multiplied by D. So the motor voltage will be changing according to the duty ratio. And then obviously you can see the voltage appear on the transistor is also a square wave. Transistor voltage is square wave, like that. The peak voltage, VDC, why I need to mention peak voltage? Because when you design a motor driver, you need to know what kind of voltage appear on the transistor to buy what kind of voltage rating for transistor. So that means this waveform will be important. So for example, if your VDC are using 100 volt, you know transistor will equal to this voltage. You need to buy transistor have 100 volt voltage rating. So that waveform will provide to you how we're going to design the motor driver. So for instance, in here, you can see that this is this voltage will going to appear on the transistor when the transistor being turned off. So if your motor driver working at 800 volt, you need to buy a transistor at least 800 volt so that it can survive for high voltage rating. If your motor only 40 volt, this will going to be 40 volt. So that's the thing you need to be careful. So even the voltage applied to the motor is square wave, but the current IA still a DC. Yeah, because we say it's inductive component, it's still a DC, but however, we're going to talk about it later, it could have a ripple because it's inductive component. There will be some changing. So we're going to examine what is that. So we got different level. Here will be basic level. You see the basic operation for motor. We still consider motor as a DC, but later on when we talk about more detailed operation or ripple, then we understand more about that. Okay, any other question? If not, we stop here. So you give you refreshing for your DC motor you learned in the past, but we do it. You can be think about how you compare your learning to the past. So that's all. Thank you.